We're going to be going up and down the Quinnipiac River, starting at the inland side, ending up down at Long Island Sound, and trying to understand that little piece of the hydrologic cycle. Remember, water is evaporating from the oceans, getting carried by the winds over the continents, raining out. Some of that rain evaporates, goes back into vapor, but the rest of it goes into the rivers and heads back towards the ocean. It's that little piece where some of it is returning back to the ocean that we'll be studying today. We'll start up north in North Haven, where if you have a map here, which you do, we'll be starting up at the north end where the river is just a little freshwater stream, not very impressive, and then gradually it comes down into the Quinnipiac salt marsh, spreads out, starts to mix with seawater brought in by the tides, and eventually we'll find it flowing out into Long Island Sound here down to our last stop, which is Fort Nathan Hale. The two primary factors that are control what we see today are the freshwater discharge in the river, which depends on whether it's rained recently and what season of the year we're in, and the phase of the tide coming in from the ocean side. So you've got one control from the land side, that's the river discharge, and the other control from the seaward side, that's the phase of the tide. Now, I've given you here, if you flip through your lab, let's see, you've got information here about the phase of the tides, which you will need to refer to as quickly as you can. So by the time we get to the first stop, I'd like you to know where we are in terms of the tides, the phase, and then also look at this plot, which will give us the river discharge over the last few weeks. Of course, it can't give us right up to the moment because I had to download this a few hours ago, so it doesn't have the latest data in it, but you can see how the river discharge has been fluctuating with Hurricane Irene, with other rain events that we had, and you'll see that it's now tapering off a little bit. Still though, much higher than usual. If you look at these triangles at the bottom, those are the typical river discharges on these dates. So the river's going to be up a little bit from normal, but yet down from some of these rather intense events we've had over the last few weeks.
Why is it so much higher than normal?
Because there's been a lot of rain over the last few months that's slowly coming out of the soil and going into the rivers. Do we have GPS readings yet? No.
Still locating satellites.
Well, let me try myself, and then we'll, if we can't get it, we'll just go on to our next site because we don't have too much time to prepare. None of the three have a, isn't there a third one? Yeah. And you don't have a data.
Mine turned itself off.
Let me see. Yeah, it may be these were used in some distant location recently. I took one to Scotland, somebody else took them to Indonesia, and they may not know. Was that you?
Yeah.
Anyway, they may not know yet that they're back in New Haven, so and make them. So let's get on the bus and go to our first stop, and we'll get some readings there. First of all, become familiar with this map. It has terrain in color, roads in white, rivers in blue, and the watershed boundaries in black. Now, there are three rivers that come into New Haven Harbor, and they are shown on this map. There's the West River, the Mill River, and the Quinnipiac River. Please locate those, and we are going to be studying the Quinnipiac River today. Remember, the watershed boundaries are important because if a raindrop falls on one side of the boundary, it goes into one river. If it falls on the other side of the boundary, it goes into the other river, because these watershed boundaries are on the high points that separate these watersheds, the divides, if you like. So become familiar with the watershed boundaries for these three rivers, and especially the Quinnipiac River. And notice how the terrain fits in with these watershed boundaries, how these black lines, the watershed boundaries, tend to follow along the higher parts of the terrain. On the last page, there is a satellite image of the area we'll be studying. And you can flip back and forth between the two pages to get a sense for where you are. But the Quinnipiac River is the river here. The Quinnipiac salt marsh is the big green blob here. And then it goes on into New Haven Harbor, which is right there. So check that out and become familiar with it. We've got about 10 minutes until we get to our next stop, our first stop. Passes down towards New Haven Harbor. That's that one, right? The middle one, yeah. The geography is pretty complicated here because roads crisscross everywhere. So it's not always trivial to know where you are on a simple map like this. So as we come around here, on your left, in just about 10 seconds, you'll see a small river heading that way. That's the Mill River. That's the middle one of the three. That's the Mill River. Then we're going to get up on the highway and we'll see the Quinnipiac River up ahead of us. The Mill River is the one that comes down from Lake Whitney. If you've been up that way. Okay, so here's I-91 North. It'll probably show up here as a, I think it's that one right there.
This is the big one?
Yeah, I think it's that one. And look to your left. That big flat area over here, that's the Quinnipiac salt marsh. The river meanders back and forth through that salt marsh. You see it's about 2 miles to the other side of it, and then the terrain starts to go up again. So that flat part is the Quinnipiac salt marsh, and you'll see it on your map and your image with the river meandering through it. Let me show you where we are. Can I borrow yours again?
Oh, absolutely.
We are right about there. Everybody see where I'm pointing? Everybody see that? This would be stop, well, on the table I guess it's stop number 2, but it's really our first stop on the river. Actually, it's where that little blue dot is in the middle of the white road. Does that show up? Yeah. And just to orient you, north, south, east, west, and this is the Quinnipiac River. So before we do much discussion, I'm sorry?
Is north like this way on the map?
North is more or less up, more or less north, yeah. Let's get our data. So we hope latitude, longitude. We need to get a water sample, and Meng has bottles, and we need salinity and temperature of the water, and temperature and humidity of the air from the Kestrel. So everybody get to work, and let me work with you're part of that team, right? So you may have the toughest job. You've got to get down there and get a sample of this stuff without falling in or making yourself all muddy. And I don't quite know how you're going to do that.
Okay.
But these little outcrops are good of concrete, but then we run out of them down there. Let me hold everything I can possibly hold to help you. And if you want a hand up.
Do you want to get sort of like underneath?
It doesn't matter too much, but try to get it full if you can. As full as you can. Beautiful. Well done. Very graceful.
Thank you.
Graceful. Now, can you grab that again? So this gadget, once it's turned on, which it's on, you need to basically just swill that around in there until these measurements start to settle down, and it'll never reach an exact constant. But while you're doing that, you take it. So we've got a conductivity meter here. The way we're measuring salinity is with a little device that measures electrical resistance as electricity flows through the water from one electrode to another. And the units for conductivity is the Siemen. I believe it's spelled S-I-E-M-E-N. There's a famous chemical company by that name, S-I-E-M-E-N, named after the same German scientist that got his name on this one. However, we are going to be reading either in millisiemens, which is 10 to the minus 3, or microsiemens, which is 10 to the minus 6 conductivity units. So when you're reading this, try to figure out if it's a little mu, which would be micro, or a little m, which would be milli. Is it? Yeah, it's going to be micro here. So has it settled down at all?
It's hovering around 350.
Push it in a little bit further. Okay.
Yeah.
Okay, why don't you read out a temperature and a conductivity, so everybody can write it down.
Okay, conductivity is 350 microsiemens, and the temperature is about 18 degrees Celsius.
Everybody get that?
18.0 degrees Celsius.
Okay. Now it might be we can put that water in there to save us having to get a separate trip. We're saving a water sample. We're going to have the chemistry done. We'll know what the chemical compounds are dissolved in this water. We won't have that data this afternoon, but we'll have it in time for your second lab meeting. Anybody have a position yet? Nobody has a position.
Yes.
GPSs are not working for me today.
Sorry.
Keep going.
I just need.
Are you indoors now? Hold on a second. Let me look at that one. Are you indoors now? No. Who else has a GPS?
For air temperature, I have 27.9 degrees Celsius.
That's fair. You almost got me.
Just have to keep waiting on those. Weak signal, need a clear. Who has the other GPS unit?
Here.
Waiting for satellites. We're going to keep waiting. That's all we can do. If we don't get data, we'll get it from another group. We'll get it now, if you've got that data, is you've got full data all the way across here? Okay, except for that. Okay, salinity. The way you do that is to basically multiply by what?
0.5 and then 10 to the minus.
Yeah, that's right. So that'll be 0.175 parts per thousand. Does anybody know what the salinity of seawater is? Salinity of seawater? 35 parts per thousand. So the salinity is not zero, but it is very small compared to seawater salinity. Why is there any salt at all? We're far from the ocean. Why is there any salt dissolved in this water?
Decaying organisms and
Yes,
Like running over rocks and then
that's right. The rain has fallen into the soil, and as it's moved through the soil, it has dissolved a little bit of material that you now find in that water. So that's just a little bit of dissolved material from the rocks. The reason why that's important, though, is because over geologic time, that tiny bit of dissolved material will concentrate in the oceans. A little bit goes in. When it evaporates, it leaves everything behind. You just get the water coming off. A little bit more goes in, and over, 6 billion years of Earth history, you build up the salinity of the oceans. So this little bit that you're measuring is very important because it is the ultimate source of the salinity in the oceans. That's why we measure it. Now, we want to get a sense for what the river is doing as well. First question I have for you, is there any sign of salt-tolerant species at this location? Any sense that there's any, we get a very low salinity at the present time, but maybe on some other days you get salt up here, but if that were the case, you would see salt-tolerant species growing here. Does anybody know enough botany to tell me whether we see any of those? Well, I'll tell you, we don't. We don't find any salt. We will at almost every other stop, but here we find just freshwater competitive species. I want to get an estimate for you, or want you to get an estimate of the discharge and compare that with what the value is on the plot that I've given you. And here's what you need to do. Estimate that width in meters. Make a guess as to the depth. That'll give you the cross-sectional area of the river. And then multiply it times the speed of the flow. That's going to be a length times a length times a speed. It's going to have units of cubic meters per second, which is a discharge for a river. So how wide would you say that river is?
15 meters.
15 meters. Let's try that. And how deep do you think it is? This is the hard part, because you really have no idea. But you can kind of see how it goes in, you know, and...
I'd say like 3 meters.
I'd say 2. Let's try 2 meters. And remember, it's a triangle, so it's going to be the width times, it probably slopes down to the middle and slopes up. So it's probably half of that, right? So, and then what is the flow speed? You want to guess the flow speed? Look at the leaves. Well, try to imagine a meter. So how many meters does one of those leaves travel in a second?
In a second?
Yeah. We want it in meters per second.
A third to a quarter?
A third to a quarter? What do you say for speed?
Like 1 meter in 4 seconds.
I think it's
A quarter meter per second.
I think it's faster than that, guys. I think it's going.
A meter per 2 seconds.
Okay, so a second is like 1 Mississippi, 2 Mississippi. So 1 Mississippi, 2 Mississippi. All right, so I think it's between a half and a full meter per second, something like that.
But the surface speed is different from the...
True. So there again, we're going to be overestimating it if we use the surface speed, because for example, look here near the shore. See how slow that is? And near the bottom where there's friction, it's going a little bit slow as well. So you might want to cut that value in half too when you're computing a discharge. Now, I admit to you, this is a very rough way to do it. But I want to give you the sense that this is basically an easy physical quantity, at least to understand, if not to measure. It's just the volume flow rate, and the plot that you have is in units of cubic feet per second. So you're just going to have to do that conversion to compare it with what you have over here. According to this, we have a discharge somewhere around 200, 3, 4, 5, yeah, about 200 cubic meters, cubic feet per second, if I've read that right. So you're going to want to compare that with the estimate you have just done. So are there any questions about this site?
Is there a way for the ocean to increase salinity like without the rivers bringing salt, just from getting salt from whatever's in the...
Not that I know of. I can't think of any offhand. You're thinking it could dissolve something from the bottom, but remember, most of the bottom stuff has come from the ocean. The ocean is putting that stuff down there.
Right.
So it's not likely to get too much more back up from it. That stuff has already been dissolved, or particles carried around in the ocean for a while. It would have picked up anything already before it fell to the bottom. In fact, the opposite. When this stuff falls to the bottom and then another layer falls on top of it, it kind of gets sequestered. It gets cut off from the ocean itself. So, no, it's hard to imagine where the ocean gets anything from except this. I'm not saying that this river is necessarily the same as all the others. There may be more or less salinity in this river than others, but basically the principle is the same. This river is like 1,000 or 1,000,000 other rivers flowing into the ocean, each carrying a little bit of dissolved material with it.
Did you say seawater is 32?
35,
35.
right. But be aware, our last stop today is not full ocean. It's full Long Island Sound. But that's not quite the same as full ocean. So we will not get up to 35 today. We'll wait and see what we get to today, but I don't think it'll be 35. Other questions about this site?
So if we're supposed to indicate tide phase,
So in this case, remember, so the river is flowing from left to right. That's north and that's south. So this flow is downriver towards Long Island Sound. Now that seems like a very trivial statement, downriver. We're probably going to see places in the river today where it's flowing back up. Once we get into that tidal influence, depending on the phase of the tides, we might see water coming back up the river, but not here. It's fresh water. I think the tide never gets here, so that's just the stately flow. And the water is fairly high compared to normal at this year, and yet not nearly as high as it was, say, a week or two ago when we had those big rain events. There the water would have been somewhere back up here. For latitude and longitude.
It's, for latitude, it's 41 degrees, 23 minutes, and 54.4 seconds.
What did you say, minute?
23 minutes and 54.4 seconds. And then longitude is 72 degrees, 52 minutes, and 4.5 seconds.
Okay, and if at the other stops we get the other ones working, we'll write down multiple numbers to compare with each other. Great, at least we got one working. Let's get back on the bus and go to the next stop. I want to be as far away from there as possible because of mosquitoes. So later on, that land was open and flat, and certain things love to be in the salt marsh. For example, factories that had a big acreage, railroads, anybody that wanted to throw their trash or their chemicals in the river would love to have a factory in the salt marsh. So as we're driving down State Street, you'll see the Quinnipiac Salt Marsh on your left. And you get a look at what's in there, including the Dow Chemical Company used to be over there. I don't think you can see the building, but we'll see buildings close to it. So there's a unique kind of development that occurred in the salt marsh because it was originally left undeveloped, then it had the advantage of being flat and with the river meandering through it. Let's get the water samples and get the data. I'd like to show everybody where we are while we're waiting. Can I do that?
Yeah, I love that.
So, we are actually, where's the sun? Let me get over here so you can see where I'm pointing. We are actually right about there. I'm going to put a little dot there. Because what's happened is that rivers come in from the north, and right here, just about 100 yards that way, it's made a right turn. And then it's going to loop around to the left. So if I orient this map, it's come down here, it's made a right turn, and then it's going to loop around to the left. So we are on the north bank, right where my pen is. You see that? We're on the north bank of the river, right where my pen is there. You see that? We're on the north bank. So it's come in just over here, made a right turn, the river has, and then it's going to make a left turn right here. So we're right in between those left and right turns. So everybody should be reading out their data and so people can write it down. Do you need some help with that? So page forward, keep going. So this one, right? Page, mark, enter.
Oh, okay.
So you're right down to the bottom.
Okay.
Oh wait.
For latitude, I got 41 degrees, 21 minutes, and 990 seconds.
And what?
Can you read that again? 890.
Let me see yours for a second.
Yeah, 41, 21, 890.
Wait a minute, I'm going to change hers because she's got degrees and then decimal minutes. So I'm going to change that.
I have 41 degrees, 21 minutes, and 53.8 seconds.
Yes, enter. And then I'm going to go that way. Right.
I have about 31.5 degrees Celsius. 31.5 degrees Celsius.
For the conductivity, it's about 1,370 microsiemens. What? Oh.
See, that's now in degrees, minutes, and seconds.
And the water temperature is 18.9 degrees Celsius.
Oops, sorry.
18.9 degrees Celsius.
Does someone have a longitude?
Yeah, it's 72 degrees, 52 minutes, and 45.9 seconds.
40.
And do we have a second latitude, longitude now?
The second latitude is 41 degrees, 21 minutes, and 53.5. And then the second
Longitude?
longitude is 72 degrees, 52 minutes, and 46 seconds.
You have all the data you need? Okay. Did you give a conductivity? Yeah. So can you convert that to salinity? I think you need to, it's here.
This is going to be harder to estimate.
What's the air temperature?
You're good for something.
The only thing.
That's it, I'm fine. I don't even know her, actually.
Okay, if everybody has a day, let's talk about the site for a second. First of all, this weed you have here is Phragmites, thank you, which is a salt-tolerant species, and of course it's all over there too. Now that stuff can outcompete other grasses when there is salt present, or some other pollution, not always salt. But so it's pretty clear, even walking up to this site, that there's some salt present. So even though we got a fairly low salinity here at the moment, this is within reach of seawater coming in from the ocean. And here we are, we're only at our second stop, but already we're getting a little bit of evidence of salt, plus a higher salinity, right, than the last time? Yeah. But in terms of the flow here, we got to figure out which way it is. Now remember, north is that way, south is that way. The river come in and bend here. So locally, that's downriver. If the water is flowing left to right here, it is moving towards the ocean. And from that little leaf, I gather that that is the case. But you've got to be careful because the wind could be pushing a leaf along like that. But I think in this case it's safe to suggest that this water is moving downriver at the moment. And do you see anything else flowing, moving along?
It kind of looks like on the opposite bank it's moving.
Like there are different currents.
Yeah, but don't be, so if you look at these little waves, then you're really going to be misled because the wind is causing those. And they could be moving with the wind rather than with the, you need to look for objects, and I think there are some objects on the far side that are moving left to right. Oh yeah, another leaf or something is coming in here. So we've got pretty good evidence that at this time the flow is downriver. So what's the phase of the tide in New Haven at the moment?
It's going from down.
So okay, so it's the tide is dropping, and that probably explains why we're getting flow downriver at this location. If the tide were rising in New Haven, we could possibly at this site be finding flow reversed, going upriver. Now, again, we should try to get an estimate of discharge. It's going to be awfully difficult, but please try to estimate a width, a depth, and if you can, a flow velocity, and compute a volumetric river discharge for this site.
Is that at least double of before?
I'd say at least double, yeah. The depth might be a little bit more as well. Unfortunately, I don't see anything out there in the middle, nor do I see anything I can throw out there. Anybody see a stick of wood or something? Do you have a good baseball arm there? Try to find something except for the underwear or whatever that is. Yeah, toss that out there as far as you can. Yeah, so it's definitely downriver. So try to get a speed from that in meters per second. That's a good marker. So our next site is going to be almost down at the other end of the salt marsh after that river has taken a few meanders. So we're likely to see some big changes down there a ways. I'll try to show you the next stop on here so you get some sense of where it is. Can I borrow someone's map? You're good for this. Once again, we are here. I believe our next stop is going to be all the way down here, almost at the other end of the salt marsh, where it begins to open out into the inner harbor and then eventually into the outer harbor of New Haven. So it's going to be approximately there for the next site. Okay? Thank you, Ann. Let's get back on the bus and we'll be on our way. We're going to make a right turn on Second Point Road, and we're going to cross over the Quinnipiac, over the bridge you see right there to your, well, that's a building, but there's a bridge over there that goes across there. We're going to cross over that, so you get a look at it just before it reaches the stop we were at. So here we are. Where are we? Is the question. We are. So we've just come, I think we're right about there. It's just come under the bridge, right? The river comes under the bridge and then begins a big sweeping turn to the right. That's what we're seeing there. So we are just where my pin is, right there. Yeah, perfect. All right. Everybody got that? So get what data you can, but then take a good close look at the river there and try to estimate the discharge at this place. And we'll have some salinity data in just a minute. As you try to do that estimate, I think you will begin to suspect, like I do, that you're going to get a big number. right? Because it's wider here, deeper here, and it seems to be moving faster here than any place we've seen so far. So how can that be? How can there be a little trickle of a stream coming in from stop 1, and then here we are, and the water, where'd all that water come from? Why is there more water passing here than there was coming into the...
Is it from like the entire watershed kind of trickling down to one?
It's like deeper
Not
here that's,
exactly.
like, collecting, kind of, or
You're getting there. I haven't heard it quite tide. Right. So just an hour or so ago, or a few hours ago, there was a lot of water going that way. And we're here too late to see it. That water went in, accumulated in the salt marsh, and now it's flowing back out again. So this is many times the freshwater stream flow we saw at stop 1, because water from the ocean has gone in, joined with that fresh water, and is now moving back out. And there's much more of it than there was fresh water at stop 1. So try to do your estimate.
For air time, I have 26.7 degrees Celsius.
for latitude I have 41 degrees, 19 minutes and 9.6 seconds. And for longitude I have 72 degrees, 53 minutes and 21.4 seconds.
Wait, can you say this again?
72 degrees, 53 minutes and 21.4 seconds for longitude. And 41 degrees, 19 minutes, 9.6 seconds for latitude. 9.6? Yeah.
And then I have for latitude 41 degrees, 19 minutes, and 10.1 seconds.
That's clever, yeah. So what do you have?
So far, 31.8. Siemens. And 21 degrees Celsius.
What did you say it was?
31 millisiemens and 21 degrees Celsius.
So converting that to salinity, can someone do that for me? What do you divide by 2?
Like
0.5.
Yeah. Okay, so that's a big, what was the salinity at the last stop?
0.685.
0.6. So more fish. Write that down. More fish. Okay. Species?
Minnows. Yeah, minnows.
Little ones like this.
So we've had a huge jump in salinity here, which proves my point that this water coming out of here is not stream water. This is ocean water that has rushed in and is now rushing back out as the tide begins to drop. And that salinity proves that. Any questions on this stop? We're a little bit behind time, so I want to, I think, have a sprint to the bus, unless there are questions.
I said 60. 60?
60 meters, possibly, yeah.
And then how deep are we?
Whatever you think.
10 meters?
10 meters? That's like 30 feet.
Probably half that, 5 meters. Yeah.
Are you gonna half this off sometimes? Is it 1 meter?
I'd say at least, yeah. Maybe 2 meters per second, I think, yeah. This stuff's really moving.
This seems less triangle-y, right?
Less
Less of a
triangle?
deeper in the-
Maybe. Hard to say.
like 2 meters triangle.
Pretty big difference.
Okay, I think we'll head back on the bus and we'll head for the next stop, which is not far from here. It's only about a mile around the bend and on the other side. So, do you have your data?
Yeah.
We're just waiting for the salt. But so this is a very wide, the river has opened up into really a harbor here. And it's very hard to tell the flow. The little waves you're seeing there are just responding to the wind. But please, look at these little buoys. They are fastened to the bottom and then they're tipping with the current. So they're giving you a good sense of the current direction and that is downriver, right? The harbor in Long Island Sound is to our left. We've crossed over the river, remember? We're on the other side, so downriver is that way. And so there's going to be a bigger influence of the ocean the further we get towards the sound. And I'm waiting to see what our salinity values are here.
29.8 millisiemens for the salinity and 20.5 degrees Celsius for the water temperature.
That's lower salinity.
That's even slightly lower salinity, yeah. So there are little eddies of fresh and salt water kind of mixing around in here, and we happen to be hit one that's slightly fresher than the one we were in over there. But I think, so this is our next to last stop. Our last stop, we can see if the salinity jumps up another level. Any questions about this site? You get a good view of where we come. You can even see the Giant's Head right through the gap there. And you can see the dump of the hill. So you know where you are. That's I-91 there. You can tell where we've come from. And now we're going to head south into the outer harbor. And we're going to end up right down near the edge of your map. We're going to end up right down here somewhere.
Right now.
Okay, let's get our data.
Are we doing the discharge flow? Or?
Well, that probably is going to be impossible. That's a good point. I don't think we can do that, but let me show you where we are, just so you know, and I know. So we are,
Here?
no, I think we're way down, I think we're way down here now. Right there. Right, yeah, exactly, right there. And Lighthouse Point, you can't, yeah, there's the lighthouse. You see it? It's hidden by the trees, but there's the lighthouse right there. So this is a big bay, you see? It's this big bay right here that we're in.
So then the lighthouse is here?
Right, exactly. That's where Lighthouse Point is, yeah. That's right, just come around the bay. So the harbor is opened way up now, so we are essentially in Long Island Sound. Okay, officially we're still in New Haven Harbor, but in terms of the water, this is as far as we go. In other words, this water would be essentially the same as Long Island Sound water, which however is not ocean water, because the connection between Long Island Sound and the ocean, which is down at the east end of the state, is fairly narrow, and the mixing is not very efficient. And so this never reaches 35 parts per thousand. We will see in a minute what it does reach, but I don't think it'll get to full ocean salinity.
So for latitude, I have 41 degrees, 16 minutes, and 8.1 seconds. 8.1 or 8. For longitude, I have 72 degrees, 54 minutes, 7.9 seconds. Huh? 7.9. Yeah.
For air temp, I have 24.5 degrees Celsius.
Good time.
What's the time?
3:20.
If you're writing down times, be sure you put what the time system is.
Yeah.
Eastern Daylight Time, yeah. Has that air temperature changed very much during the day?
Yeah, we started out at 28, and we went up to 31, and now we're down to like 24.5.
So just the warming of the day, perhaps?
Yeah, or
maybe.
even, it changed a lot with the shade, I feel like.
Oh, that could be it too, yeah. That could be it too. And the water temperature has been colder though. Is that right, than the air throughout?
Yeah.
Yeah.
The conductivity is about 35.4 millisiemens, and the water temperature is 22 degrees Celsius.
How does that water temperature compare with earlier?
17 points.
The warmest.
It's warmer, yeah. Isn't that odd? So actually the stream is colder because, okay, the Long Island Sound has been storing heat all summer. And as you know from our discussion of hurricanes, right now is about its maximum temperature. Whereas the stream is just whatever happened to fall, whatever temperature that rain was when it fell a few weeks ago. And I guess that was a few degrees colder. So it's odd, but right now the stream water is colder than the stored heat that's in the in Long Island Sound. And what does that make the salinity then?
17.7.
17. So I thought we were getting closer to 20, but we're pretty close to 20. So I think that's what we're, that's going to be essentially Long Island Sound salinity, 17 parts per thousand. Are there any questions about this site? What do you see out there?
What's that light rising out? Like it kind of juts out of the water.
Yeah, that's a breakwater. That's a stone wall. There's 3 of them actually. There's another one over there. That's a little, another little lighthouse at the end of the. That's a breakwater, so the waves don't come into the harbor and make the ships rock at their pier. So you got everything? Okay. I'd like to stay, but it's beautiful here. But let's get back on the bus and get back to the university site because we don't have too much time to prepare. None of the 3 have a. Isn't there a third one? Yeah. And you don't have a data.
Mine turned itself off.
Let me see. Yeah, it may be these were used in some distant location recently. I took one to Scotland. Somebody else took them to Indonesia, and they may not know. Was that you? Yeah. Anyway, they may not know yet that they're back in New Haven. So and make them. So let's get on the bus and go to our first stop, and we'll try to get some readings there. First of all, become familiar with this map. It has terrain in color, roads in white, rivers in blue, and the watershed boundaries in black. Now, there are 3 rivers that come into New Haven Harbor, and they are shown on this map. There's the West River, the Mill River, and the Quinnipiac River. Please locate those, and we are going to be studying the Quinnipiac River today. Remember, the watershed boundaries are important because if a raindrop falls on one side of the boundary, it goes into one river. If it falls on the other side of the boundary, it falls from the seaward side. That's the phase of the tide. Now, I've given you here, if you flip through your lab, let's see. You've got information here about the phase of the tides, which you will need to refer to as quickly as you can. So by the time we get to the first stop, I'd like you to know where we are in terms of the tides, the phase, and then also look at this plot, which will give us the river discharge over the last few weeks. Of course, it can't give us right up to the moment because I had to download this a few hours ago, so it doesn't have the latest data in it, but you can see how the river discharge has been fluctuating with Hurricane Irene, with other rain events that we had, and you'll see that it's now tapering off a little bit. Still though, much higher than usual. If you look at these triangles at the bottom, those are the typical river discharges on these dates. So the river's going to be up a little bit from normal, but yet down from some of these rather intense events we've had over the last few weeks.
Why is it so much higher than normal?
Because there's been a lot of rain over the last few months that's slowly coming out of the soil and going into the rivers. Do we have GPS readings yet? No.
Still locating satellites.
Well, let me try myself, and then we'll if we can't get it, we'll just go on to our next. It goes into the other river because these watershed boundaries are on the high points that separate these watersheds, the divides, if you like. So become familiar with the watershed boundaries for these 3 rivers, and especially the Quinnipiac River. And notice how the terrain fits in with these watershed boundaries, how these black lines, the watershed boundaries, tend to follow along the higher parts of the terrain. On the last page, there is a satellite image of the area we'll be studying. And you can flip back and forth between the two pages to get a sense for where you are. But the Quinnipiac River is the river here. The Quinnipiac salt marsh is the big green blob here. And then it goes on into New Haven Harbor, which is right there. So check that out and become familiar with it. We've got about 10 minutes until we get to our next stop, our first stop. Pass is down towards New Haven Harbor. That's that one, right, the middle one, yeah. The geography is, we're going to be going up and down the Quinnipiac River, starting at the inland side, ending up down at Long Island Sound, and trying to understand that little piece of the hydrologic cycle. Remember, water is evaporating from the oceans, getting carried by the winds over the continents, raining out. Some of that rain evaporates, goes back into vapor, but the rest of it goes into the rivers and heads back towards the ocean. It's that little piece where some of it is returning back to the ocean that we'll be studying today. We'll start up north in North Haven, where if you have a map here, which you do, we'll be starting up at the north end where the river is just a little freshwater stream, not very impressive. And then gradually it comes down into the Quinnipiac salt marsh, spreads out, starts to mix with seawater brought in by the tides, and eventually we'll find it flowing out into Long Island Sound here down to our last stop, which is Fort Nathan Hale. The two primary factors that are control what we see today are the freshwater discharge in the river, which depends on whether it's rained recently and what season of the year we're in, and the phase of the tide coming in from the ocean side. So you've got one control from the land side, that's the river discharge, and the other control. Pretty complicated here because roads crisscross everywhere. So it's not always trivial to know where you are on a simple map like this. So as we come around here, on your left, in just about 10 seconds, you'll see a small river heading that way. That's the Mill River. That's the middle one of the three. That's the Mill River. Then we're going to get up on the highway and we'll see the Quinnipiac River up ahead of us. The Mill River is the one that comes down from Lake Whitney. If you've been up that way. Okay, so here's I-91 North. It'll probably show up here as a, I think it's that one right there.
This is the big one?
Yeah, I think it's that one. And look to your left. That big flat area